Have you ever seriously tried to picture it? I mean, really sit down and attempt to build a mental image of what quantum entanglement means. I've been trying, and it leaves me with this lingering feeling of, well, unease. It's a feeling I imagine is familiar to anyone who's brushed up against the edges of modern physics without the armour of advanced mathematics. It's not a lecture I'm trying to start here. It's more of a shared confusion, a stream of thought that I can't seem to shake. It starts simply enough. I read about these two particles. Let's call them particles A and B. They are created together, they interact, and then they fly off in opposite directions, perhaps travelling light years apart. The articles I read, the ones written in supposedly simple language, say they are entangled. This means that if I measure a property of particle A, say it's psimor, which I'm told is a bit like it's spinning up or down, I will instantly know the spin of particle B. If A is up, B is down, instantly. It doesn't matter if particle B is across the room or in another galaxy. And this is where the trouble starts. This is where the absurdity kicks in. Our world, the one we live in and touch and see, doesn't work that way. It's a world of common sense, a world built on sturdy rules. The primary rule is cause and effect. I push a glass, then it falls. I turn on a light switch, then the light comes on. There is a delay. Information has to travel. And as the great Albert Einstein told us, nothing can travel faster than the speed of light. This is a comfortable rule. It makes sense. It makes the universe feel large but manageable. If something happens on the sun, it takes 8 minutes for us to know about it. That's fine, it's logical. But these entangled particles seem to laugh at this rule. How does particle B know that particle A has been measured? The very word know feels wrong, but what else can I use? There is no signal sent, no email, no text message, no light speed pulse travelling from A to B. It just knows. The connection is faster than light. It is instantaneous. This is the spooky action at a distance that Einstein himself was so uncomfortable with. And frankly, I'm with him. It feels spooky. It feels like a cheat. This unsettling feeling isn't just about the speed. It's about the very nature of reality. The physicists who explore this realm tell us things that sound less like science and more like philosophical riddles. They say that before we measured particle A, it wasn't up or down. It was in some fuzzy, vague state of both at the same time, a probability cloud. This is where common sense throws its hands up and walks out of the room. My brain simply rebels against this. The chair I am sitting on is here. It is solid. It is not a probability cloud of a chair. The moon, I am quite certain, is still there even when I'm not looking at it. Our entire existence is based on the assumption that the world is real solid and behaves in a predictable way, whether we are observing it or not. But quantum mechanics, the most successful scientific theory in human history, the theory that powers our computers, our phones, our lasers, tells me that at the fundamental level, this assumption is wrong. At the very, very small level, reality is not solid. It is a game of chance. A particle isn't in one place, it has a chance of being in several places. It only chooses a spot when we, the observers, force its hand by looking. This is the source of the bat and the deep unease. It implies that our solid, reliable world is just an illusion. It suggests that the classical world of cause and effect is just what happens when you average out trillions upon trillions of these tiny, absurd quantum events. Our reality isn't the real reality, it's just a statistical approximation. It feels like standing on a bridge that I have always believed was made of solid steel, only to be told it's actually made of a swarm of chaotic buzzing insects, and it's only by sheer luck and probability that they happen to be holding my weight. This isn't a lecture. I have no equations to offer. I have no grand theories. I am just a person trying to reconcile two worlds that cannot coexist in my mind. The world I see and the world that science tells me is. When I try to think about entanglement, I'm forced to confront this. If these two particles separated by the vastness of space are still one system, if a touch on one is a touch on the other, then what does it mean to be separate? It challenges the very idea of here and there. It challenges the very idea of an individual thing. If that connection is real, then the universe is not a collection of separate objects as it appears. It is a single interconnected whole, a network. And this is the thought that circles back and keeps me awake. This is the unsettling. It's a philosophical vertigo. We are built to understand a world of rocks and trees and distances. We are not built to understand a world where two things can be in the same place at once, or where distance is a meaningless concept. This is where I am. I'm not looking for an answer, not really. I'm just trying to get comfortable with the question. I'm trying to navigate this feeling that the floor beneath my feet isn't quite as solid as I once believed. And perhaps in sharing this line of thought, this trantro, this musing, it becomes a little less unsettling. Or perhaps by sharing it, we just agree to be unsettled together. When we first learn about the world, we are taught to trust a fundamental rule: things are separate. A book on your shelf is a distinct object. The chair you are sitting on is another. They exist in their own space, and to affect one you must interact with it directly. If you want to move the book, you must touch it. If you want to tell a friend something, you must send a signal. Sound waves an email or a text that travels through space and takes time to arrive. This idea is called locality. It is the common sense foundation of our entire reality. Quantum entanglement shatters this foundation. It presents us with a new and bizarre concept: two particles, even if separated by billions of miles, can be fundamentally linked, acting as a single unified system. This is not a metaphor. It is not like two friends who know each other so well they finish each other's sentences. It is a literal physical truth. When two particles like electrons or photons are created in a special entangled way, they lose their individual identities. You can no longer speak of particle A and particle B. Instead, you must speak of the system AB. They are described by a single shared mathematical identity. What happens to one particle is what happens to the other, because they are not truly other. They are two parts of one whole, much like the front and back of a single coin. To understand this, we must use the most common property discussed in quantum mechanics: spin. You can imagine spin as a tiny internal arrow that every particle has. For the simplest particles, this arrow can only point in one of two directions when we measure it up or down. There is no sideways or halfway. It is a simple binary choice. Now here is the first quantum mystery. Before we measure a particle's spin, it does not have a definite state. It is not secretly up or down while we are not looking. Instead, it exists in a fuzzy, ghostly state of probabilities called a superposition. It is both up and down at the same time, a spinning coin that has not yet landed. The act of measuring it is what forces the coin to land, forcing the particle to choose a state. Entanglement takes this mystery and makes it a partnership. Imagine we create two particles A and B and we entangle them. We create them in such a way that their total combined spin must be zero. This is our single system. This system knows one rule: if one particle is up, the other must be down to keep the total spin at zero. Now we separate them. We send particle A to a laboratory in London. We send particle B to a laboratory in Sydney, Australia. They are now thousands of miles apart. While they are travelling, neither particle has a defined spin. Particle A is in a superposition of up-down. Particle B is also in a superposition of up-down. They are both spinning unlanded coins. A scientist in London decides to measure particle A. She sets up her detector. The moment her detector interacts with particle A, its fuzzy superposition collapses. The particle is forced to choose. The coin lands, let's say it lands spin up. Here is the shocking part. The absolute instantaneous universe-bending shock of quantum mechanics. At the exact same instant, not a second later, not a millisecond later, but immediately the scientist in Sydney measures particle B, and she finds with 100% certainty that her particle is spun down. This correlation is perfect every single time. If London finds up, Sydney finds down. If London finds down, Sydney finds up. Think about what this means. How did particle B know what particle A did? Our first logical guess, the one Albert Einstein preferred, is that the information was hidden inside them all along. He argued this was not spooky at all. It's like putting a pair of gloves into two separate boxes. You put the left glove in box A and the right glove in box B. You mail box A to London and box B to Sydney. When the scientist in London opens her box and sees the left glove, she instantly knows the Sydney box contains the right glove. No spooky action is needed. The information which glove was in which box was always there. But Einstein was wrong. Decades of experiments have proven beyond any doubt that the particles are not carrying hidden information. They are not gloves. They truly are spinning coins with no defined state. The up or down reality does not exist until the moment of measurement. This means that the act of measuring particle A in London caused particle B in Sydney to become spin down. This connection is instantaneous. It does not travel through space. It ignores the universal speed limit, the speed of light, which Einstein himself had established as the law of the land. According to Einstein, absolutely no information can travel faster than light. Yet this information, the result of the London measurement, seems to arrive in Sydney instantly, which should be impossible. This phenomenon is the heart of the mystery. It is called non-locality. Local means an object can only be influenced by its immediate surroundings. Non-local means an object can be influenced by something happening far away with no connection through the space in between. Entanglement shows us that our universe is non-local. The two particles are not two things, they are one thing. The single system they form does not exist just in London or just in Sydney. The system itself is non-local. It exists outside of our normal boundaries of space. The thousands of miles separating the two particles are to the system itself completely irrelevant. The system A plus B is a single entity, and when you poke one part of it, measure A, the entire entity responds at once, including the part we call B. The particles are not sending secret faster than light messages to each other. They do not need to. They are already and always have been in perfect communication because they are not in communication at all. They are one and the same. The separation we see in our three-dimensional world is an illusion. In the deeper quantum reality, they have never been apart. While quantum mechanics was proving incredibly successful, one of its original architects was becoming its greatest critic, Albert Einstein. Einstein's entire career was built on finding a deep, orderly, and predictable set of rules for the cosmos. His theory of relativity described a universe of elegant cause and effect. But this new quantum theory, which he had helped to start, described a world built on fundamental randomness, probabilities, and uncertainty. This deeply bothered him. He respected the theory's power; it correctly predicted the results of experiments. But he felt that its description of reality was disturbing and, more importantly, unfinished. This led him to ask the central question of his later life: is quantum mechanics complete? When physicists use the word complete, they mean, does this theory tell us everything there is to know about a system? Or is it just a useful statistical tool that hides a deeper reality we haven't found yet? Einstein believed in the second option. He famously stated, God does not play dice with the universe. He refused to accept that the universe's fundamental nature was based on a coin flip. He argued that when quantum mechanics tells us there is a 50% chance a particle will be spin up and a 50% chance it will be spin down, it is not because the particle is in a fuzzy state of both. He believed it is because we are missing information. Think of it this way. If you flip a coin, you call it a 50-50 chance. But that is only because you do not have enough information. If you knew the exact force of the thumb flick, the starting rotation of the coin, the air resistance, and the table's bounciness, you could in theory use the laws of classical physics to predict heads or tails with 100% certainty. The randomness, was just a cover for our own ignorance. Einstein believed the same must be true for quantum particles. In 1935, Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, published a famous paper that became known as the EPR paradox. This paper was not an experiment, it was a thought experiment, a brilliant logical argument designed to expose a fatal flaw in quantum theory and prove it must be incomplete. The argument centered on a strange quantum phenomenon called entanglement. Here is the setup. Imagine a special kind of particle that has zero spin, a type of angular momentum. This particle then decays, breaking into two new smaller particles. Let's call them particle A and particle B. These two new particles fly off in opposite directions at high speed. Because they were born from the same event, these two particles are entangled. This means their properties are linked in a very special way. The rules of their creation demand that their spins must be opposite. If particle A is measured to be spin up, particle B must instantly be spin down. If particle A is spin left, particle B must be spin right. They're a perfectly correlated pair. Now here is where the paradox comes in. According to the standard rules of quantum mechanics, the Copenhagen interpretation championed by Niels Bohr, a particle does not have a definite spin until it is measured. Before measurement, particle A is in a superposition of all possible spins both up and down at the same time. The same is true for particle B. Let's wait until particle A is in a lab on Earth and particle B has travelled all the way to a lab on the Moon. They are now thousands of miles apart. A scientist on Earth, Alice decides to measure particle A. The moment she measures it, its fuzzy superposition collapses. The dice are rolled and the outcome is spin up. Because the particles are entangled, Alice instantly knows at that very same moment that particle B on the Moon must be spin down. But wait, according to quantum theory, particle B also did not have a definite spin until this moment. This implies that Alice's measurement on Earth instantaneously forced particle B on the Moon to snap into the spin-down state. This information, the knowledge of what Alice did, seemed to travel from Earth to the Moon instantly faster than the speed of light. This is what Einstein famously mocked as spooky action at a distance. He could not accept it. It violated his own theory of special relativity, which set the speed of light as the absolute speed limit for anything, including information. How could the particle on the moon know what happened on Earth faster than light could get there? Einstein, Podolsky, and Rosen offered a different, much simpler explanation. Their argument was that the spooky action was just an illusion. The particles already had their properties determined from the very beginning. This is the theory of hidden variables. Einstein argued that the particles were carrying a hidden instruction sheet from the moment they were created. Particle A was always going to be spin up, and particle B was always going to be spin down. We just did not know it until we looked. The act of measuring did not create the state. It simply revealed the state that was there all along. The easiest way to understand this is with an analogy. Imagine I have a pair of gloves, one left and one right. I put each glove into a separate identical box. I give one box to Alice on Earth and one box to Bob on the moon. Alice opens her box and sees she has the left glove. Does she spookily know what Bob has? Yes. She knows instantly that Bob has the right glove. Did her act of opening the box cause Bob's glove to become the right glove? Of course not. That would be ridiculous. The gloves had their gloveness, left or right, determined from the moment I put them in the boxes. Einstein argued that the entangled particles were just like the gloves. There was no spooky action. There was just pre-existing hidden information that the quantum theory was failing to describe. This worldview is called local realism. This is the glove part. Objects have definite real properties like spin up or left glove before we measure them. The moon is still there even when you are not looking at it. Locality. This is the no spooky action part. What Alice does in her lab opening the box can only affect things in her immediate local area. It cannot instantly influence what is happening on the moon. The EPR paper presented a stark choice to the world of physics. Either quantum mechanics is incomplete, there are hidden variables like the gloveness that determine everything, and our current theory is just a statistical approximation. This is what Einstein believed. Or quantum mechanics is complete, which means the world is not locally real. Spooky action at a distance is a real phenomenon, and the universe is built on a type of interconnectedness that defies all common sense. For decades, this was just a philosophical argument. Niels Bohr, Einstein's great rival, argued that Einstein's definition of reality was the problem. But no one knew how to design an experiment to settle the debate. Who was right? Was it Einstein's common sense hidden gloves, or was it Bohr's spooky action? It seemed like a question that science could never answer. For decades, the very soul of physics was trapped in a philosophical stalemate. Following the challenging thought experiment proposed by Einstein, Podolsky, and Rosen, known as the EPR paradox, the world of science was split into two camps. On one side stood Albert Einstein, who, despite being a founder of quantum theory, could not accept its deepest implications. He insisted that the theory was incomplete. He argued for a reality built on what we now call local realism. This is a two-part idea that feels like pure common sense. Realism is the belief that objects have definite properties before we measure them. A ball has a position even if you aren't looking at it. Locality is the belief that nothing can travel faster than the speed of light, meaning an action in one place cannot instantly affect a distant place. Einstein championed hidden variables, unknown instructions or properties, hidden within particles that decide their behavior in advance, creating the illusion of quantum randomness. On the other side was Niels Bohr and the Copenhagen interpretation. Bohr argued that it was meaningless to even ask what a particle was before you measured it. The act of measurement, he claimed, is what creates the reality. The particle existed only as a fuzzy cloud of probabilities, and its spooky connection with its entangled twin was just a feature of this strange quantum world. The problem was, this was just a debate. It was philosophy, not science. Both Einstein's hidden realism and Bohr's fuzzy probability predicted the exact same outcomes for any experiment anyone could think of. You couldn't test it. Einstein's idea was an untestable belief, and Bohr's was a philosophical shrug. This deadlock lasted for 30 years from the 1930s to the 1960s, and the question was pushed aside as metaphysics. Then in the 1960s, a brilliant physicist from Northern Ireland named John Stuart Bell entered the scene. Working at CERN, the European Particle Physics Laboratory, Bell was deeply fascinated by this old dusty argument. He, like Einstein, felt uncomfortable with the spookiness of quantum mechanics. He wondered if Einstein's hidden variables idea could be true. But unlike everyone before him, Bell decided to stop arguing and start calculating. He set out to turn this philosophical debate into a testable mathematical question. What he discovered would change the world. His central idea was a stroke of genius. Bell did not try to prove Einstein right. Instead, he asked if Einstein is right. If local realism is the true law of the universe and particles really do carry hidden instructions, what would be the consequences? Bell created a thought experiment very similar to the EPR paradox. Imagine a machine that produces pairs of entangled particles, let's call them particle A and particle B. Particle A is sent to a detector on one side of the room, and particle B is sent to a detector on the far side. Each detector can be set to measure a property like the particle's spin. Think of it as which way the particle is pointing. Crucially, the detectors have multiple settings. The experimenter on the left can choose to measure spin along, say, a vertical axis, a horizontal axis, or a diagonal axis. The experimenter on the right can do the same, and they choose their settings randomly and independently for each pair of particles. Now here is Bell's core logic. If Einstein is right local realism, then each particle left the machine with a hidden instruction set. Particle A's instructions might say, if measured on the vertical axis, point up. If measured on the horizontal, point down. If measured on the diagonal, point up. His twin particle B would have a corresponding set of instructions. The measurement doesn't create the spin, it just reveals what was already there. Bell used basic probability, the same kind of math you would use for coin flips or dice rolls to calculate what would happen. He proved mathematically that if this hidden instruction set exists, there is a strict limit on the amount of correlation the two experimenters will find when they compare their notes later. For example, the number of times they get the same answer when one measures vertically and the other measures diagonally combined with other setting. Comparisons cannot exceed a certain number. This mathematical limit is known as Bell's inequality. It is a fundamental speed limit for reality if reality is based on local realism. It is the logical line in the sand that common sense cannot cross. But Bell wasn't finished. He then asked the next billion-dollar question, what does quantum mechanics predict for this exact same experiment? He ran the calculations using the spooky math of quantum theory, where the particles have no set properties until measured, but are linked by entanglement. The answer was shocking. Quantum mechanics predicted stronger correlations. It predicted that the number of matching answers would be higher than Bell's common sense limit. Quantum mechanics predicted that reality would violate Bell's inequality. Suddenly the philosophical debate was over. It was now a physical experiment. The question was no longer which idea is nicer. The question was, what is the number? Bell had provided a recipe for an experiment that would force nature to show its hand. It took years to build experiments sensitive enough to perform this test. In the 1970s and 80s, physicists like John Clauser and most famously Alain Aspect in France conducted the experiments. They used photons, particles of light as their entangled pairs. Aspect's 1982 experiment was incredibly clever. He changed the detector settings while the photons were already in flight, guaranteeing that one detector couldn't somehow know the setting of the other. The results started to come in, and they were staggering. Again and again, the experiments showed that Bell's inequality was violated. The correlations between the particles were stronger than local realism could ever allow. The experimental results perfectly matched the spooky predictions of quantum mechanics. Over the following decades, these experiments were repeated with more and more precision, closing every conceivable loophole. Scientists worried that perhaps the detectors weren't efficient enough, the detection loophole, or that the settings weren't truly random, the freedom of choice loophole. By 2015, multiple teams had conducted loophole-free Bell tests, and the verdict was unanimous. The conclusion is one of the most profound in the history of human thought. Local realism is false. The common sense view of the universe that Einstein and the rest of us instinctively believe in is wrong. The universe does not operate on the principles of local realism. This means one of two pillars of our intuition must fall. Either locality is false and spooky action at a distance is real, with one particle's measurement truly and instantly affecting its partner regardless of distance, or realism is false and particles do not have definite properties before they are measured. The moon in a very real sense may not be there when no one is looking. Most physicists have come to accept that realism is the component that is wrong. The universe at its most fundamental level is not a clockwork machine with hidden gears. It is a world of pure potential and probability where properties are only brought into existence by the act of interaction and measurement. Einstein's hidden variables do not exist. The EPR paradox, which Einstein designed to show that quantum mechanics was incomplete, was turned by John Bell into the very tool that proved Einstein wrong. Nature really is spooky. D. For decades, the very soul of physics was trapped in a philosophical stalemate. Following the challenging thought experiment proposed by Einstein, Podolsky and Rosen, known as the EPR paradox, the world of science was split into two camps. On one side stood Albert Einstein, who despite being a founder of quantum theory could not accept its deepest implications. He insisted that the theory was incomplete. He argued for a reality built on what we now call local realism. This is a two-part idea that feels like pure common sense. Realism is the belief that objects have definite properties before we measure them. A ball has a position, even if you aren't looking at it. Locality is the belief that nothing can travel faster than the speed of light, meaning an action in one place cannot instantly affect a distant place. Einstein championed hidden variables, unknown instructions or properties hidden within particles that decide their behavior in advance, creating the illusion of quantum randomness. On the other side was Niels Bohr and the Copenhagen interpretation. Bohr argued that it was meaningless to even ask what a particle was before you measured it. The act of measurement, he claimed, is what creates the reality. The particle existed only as a fuzzy cloud of probabilities, and its spooky connection with its entangled twin was just a feature of this strange quantum world. The problem was this was just a debate. It was philosophy, not science. Both Einstein's hidden realism and Bohr's fuzzy probability predicted the exact same outcomes for any experiment anyone could think of. You couldn't test it. Einstein's idea was an untestable belief, and Bohr's was a philosophical shrug. This deadlock lasted for 30 years from the 1930s to the 1960s, and the question was pushed aside as metaphysic. Then in the 1960s, a brilliant physicist from Northern Ireland named John Stuart Bell entered the scene. Working at CERN, the European Particle Physics Laboratory, Bell was deeply fascinated by this old dusty argument. He, like Einstein, felt uncomfortable with the spookiness of quantum mechanics. He wondered if Einstein's hidden variables idea could be true. But unlike everyone before him, Bell decided to stop arguing and start calculating. He set out to turn this philosophical debate into a testable mathematical question. What he discovered would change the world. His central idea was a stroke of genius. Bell did not try to prove Einstein right. Instead, he asked if Einstein is right, if local realism is the true law of the universe and particles really do carry hidden instructions. What would be the consequences? Bell created a thought experiment very similar to the EPR paradox. Imagine a machine that produces pairs of entangled particles, let us call them particle A and particle B. Particle A is sent to a detector on one side of the room and particle B is sent to a detector on the far side. Each detector can be set to measure a property like the particle's spin. Think of it as which way the particle is pointing. Crucially, the detectors have multiple settings. The experimenter on the left can choose to measure spin along, say, a vertical axis, a horizontal axis, or a diagonal axis. The experimenter on the right can do the same, and they choose their settings randomly and independently for each pair of particles. Now here is Bell's core logic. If Einstein is right, local realism, then each particle left the machine with a hidden instruction set. Particle A's instructions might say, if measured on the vertical axis, point up, if measured on the horizontal, point down, if measured on the diagonal, point up. Its twin particle B would have a corresponding set of instructions. The measurement doesn't create the spin, it just reveals what was already there. Bell used basic probability, the same kind of math you'd use for coin flips or dice rolls, to calculate what would happen. He proved mathematically that if this hidden instruction set exists, there is a strict limit on the amount of correlation the two experimenters will find when they compare their notes later. For example, the number of times they get the same answer when one measures vertically and the other measures diagonally combined with other setting comparisons cannot exceed a certain number. This mathematical limit is known as Bell's inequality. It is a fundamental speed limit for reality, if reality is based on local realism. It is the logical line in the sand that common sense cannot cross. But Bell wasn't finished. He then asked the next billion-dollar question: what does quantum mechanics predict for this exact same experiment? He ran the calculations using the spooky math of quantum theory, where the particles have no set properties until measured, but are linked by entanglement. The answer was shocking. Quantum mechanics predicted stronger correlations. It predicted that the number of matching answers would be higher than Bell's common sense limit. Quantum mechanics predicted that reality would violate Bell's inequality. Suddenly, the philosophical debate was over. It was now a physical experiment. The question was no longer which idea is nicer. The The question was, what is the number? Bell had provided a recipe for an experiment that would force nature to show its hand. It took years to build experiments sensitive enough to perform this test. In the 1970s and 80s, physicists like John Clauser and most famously Alain Aspect in France conducted the experiments. They used photons, particles of light as their entangled pairs. Aspect's 82 experiment was incredibly clever. He changed the detector settings while the photons were already in flight, guaranteeing that one detector couldn't somehow know the setting of the other. The results started to come in, and they were staggering. Again and again the experiment showed that Bell's inequality was violated. The correlations between the particles were stronger than local realism could ever allow. The experimental results perfectly matched the spooky predictions of quantum mechanics. Over the following decades, these experiments were repeated with more and more precision, closing every conceivable loophole. Scientists worried that perhaps the detectors weren't efficient enough, the detection loophole, or that the settings weren't truly random, the freedom of choice loophole. By 2015, multiple teams had conducted loophole-free Bell tests, and the verdict was unanimous. The conclusion is one of the most profound in the history of human thought. Local realism is false. The common-sense view of the universe that Einstein and the rest of us instinctively believe in is wrong. The universe does not operate on the principles of local realism. This means one of two pillars of our intuition must fall. Either locality is false and spooky action at a distance is real, with one particle's measurement truly and instantly affecting its partner, regardless of distance, or realism is false, and particles do not have definite properties before they are measured. The moon, in a very real sense, may not be there when no one is looking. Most physicists have come to accept that realism is the component that is wrong. The universe at its most fundamental level is not a clockwork machine with hidden gears. It is a world of pure potential and probability where properties are only brought into existence by the act of interaction and measurement. Einstein's hidden variables do not exist. The EPR paradox, which Einstein designed to show that quantum mechanics was incomplete, was turned by John Bell into the very tool that proved Einstein wrong. Nature really is spooky. Let's get one of the biggest and most common misunderstandings out of the way immediately. Quantum entanglement does not allow anyone to send information faster than the speed of light. It's an easy mistake to make. The very description of entanglement, spooky action at a distance, sounds like a perfect blueprint for an instant universe-spanning telephone. If Alice measures her particle on Earth and it is spin-up, she knows that Bob's particle, even if it's in the Andromeda galaxy, has instantly become spin-down. It feels like a signal. It feels like Alice caused Bob's particle to become down, but this is not communication. To understand why we have to separate two different ideas, correlation and communication. Communication is the act of sending a chosen message. If Alice wants to send Bob the letter A, she needs a way to make his particle do something that he can interpret as A. If she wants to send B, she needs to make it do something else. The sender must have control over the contents of the message. This is where the entire idea of a faster-than-light communicator breaks down. The problem and the beautiful universe-saving solution is randomness. When Alice on Earth decides to measure her particle, she has absolutely no control over what result she will get. Before her measurement, the particle doesn't have a fixed state. It exists in a superposition, a ghostly blend of both up and down at the same time. The act of measuring is what forces the particle to choose one state. But which one will it choose? Quantum mechanics tells us the answer is purely random. For any single measurement Alice makes, she has a 50% chance of getting spin up and a 50% chance of getting spin down. She cannot force it. She can't aim her detector in a special way to make the particle land on up, just because she wants to send Bob a 1 instead of a 0. She is a passive observer of a random coin flip. Now let's look at Bob's side in the Andromeda galaxy. Let's say Alice measures her particle and gets up. Instantly, the universe-spanning connection is resolved. Bob's particle is now definitively spin down, but Bob doesn't know this. From Bob's perspective, his particle is also in a superposition. When he decides to measure it, he also has a 50% chance of getting up and a 50% chance of getting down. Wait, you might say, if Alice got up, isn't Bob guaranteed to get a down? Yes, he is, but he has no way of knowing if his down result was because Alice happened to measure up, or if Alice hasn't even measured her particle yet and his down was just his own random 50-50 chance. To Bob, his results will always look random. If he measures 1,000 particles, his list of results will look like this: down, up, down, 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 up. It will look like a completely random string of coin flips. He cannot look at his list and find any message hidden in it. He can't see a pattern. He can't look at his down result and say, aha, that's a signal from Alice. It's just a random outcome. The spooky correlation is completely hidden from both of them. Alice has a random list of results. Bob has a random list of results. Neither of them can send a single bit of information to the other. So how do they ever know the particles were entangled at all? This is the most important part. The correlation is only revealed after they compare their results, and to do that they must use a classical slower-than-light communication channel. Let's run a thought experiment. Alice and Bob synchronize their watches. They agree to measure one of their entangled particles every minute on the minute for 1 hour and write down their results. At 100 p.m. Alice measures. She gets up, she writes it down. In Andromeda at 100 p.m. Bob measures. He gets down, he writes it down. At 1:01 p.m. Alice measures. She gets down, she writes it down. In Andromeda at 1:01 p.m. Bob measures. He gets up, he writes it down. They continue this for an hour. At the end, Alice has a notebook that looks like this called Up 101, Down 102, Down 13, Up, a list that looks completely random. Bob has a notebook that looks like this one, Down 101, Up 102, Up 103, Down. His list also looks completely random. No information has been transferred. Bob's list is useless to him. Alice's list is useless to her. Now Alice takes her notebook and sends it to Bob using a traditional radio signal. This signal travels at the speed of light. If Bob is 1 light year away, it will take 1 year for him to get her message. When her message finally arrives, Bob takes his own notebook and lays it next to Alice's message. Time: Alice's result arrived 1 year later. Bob's result recorded 1 year ago. 102, you up, down 1, down up 102, down up 103, up down. Only now, by comparing the two lists side by side, do they see the perfect instantaneous spooky correlation. They see that for every single measurement their results were the exact opposite. The connection was real, but the knowledge of that connection could only travel as fast as a radio wave. No information was sent faster than light. This limit is not a bug or something scientists are trying to fix. This fundamental randomness is a core feature of the universe, and it is what protects the entire fabric of reality. It's what protects causality. Causality is the simple common-sense law that a cause must happen before its effect. You must strike a match cause before it lights effect. A window cannot shatter effect before a baseball hits it cause. Albert Einstein's theory of relativity is built on this foundation. It establishes the speed of light as the ultimate speed limit for everything that carries information. If you could break that limit, if you could really send a message faster than light, you would also break causality. If Alice could force her particle to be up and send an instant up signal to Bob, things would get very strange. According to relativity, the very idea of instantaneous is flexible. For an observer moving at a very high speed, they might see Bob receive the message before Alice even sent it. This creates impossible paradoxes. Bob could receive a message from Alice before she sent it. He could then use his own faster-than-light transmitter to send a message back to her, which would also arrive in her past telling her, "Don't send me that message." She would then receive his reply before she ever had the idea to send the original message, creating a nonsensical loop where the effect the reply happens before the cause, the original message. This would destroy the logic and the ordered flow of time. Quantum mechanics, for all its strangeness, beautifully prevents this. The absolute randomness of the measurement is the universe's firewall. It allows for the spooky connection to be real, but it locks any useful information behind a randomness key. The only way to unlock it and see the correlation is to bring the two keys, the two notebooks together, using a method that obeys the speed of light. This principle is so important that it has a name, the no communication theorem. It formally proves that you cannot use the shared randomness of entanglement to transmit any classical information. So entanglement remains one of the deepest and most wonderful mysteries of the universe. It shows us that reality is connected in ways our intuition can barely grasp. But it does not break the universe's most fundamental rule. The spooky correlation is real, but causality is and always will be safe. We have established a fact that seems to defy all common sense. Two particles separated by vast distances remain mysteriously linked. When one is measured, the other instantly knows, adopting a corresponding state. This connection is immediate, faster than light, and seemingly telepathic. This leads to the most profound question in this puzzle: what is the strength? If particle A tells particle B what to do, how does it send that message? Our entire lives are governed by cause and effect, which are linked by forces and signals. If you push a shopping cart, you apply a force. If you call a friend, you send a signal, radio waves. Both of these travel through space and are limited by the speed of light. But entanglement breaks this rule. The connection is not a force, there is no pull or push travelling between the two particles. It is also not a signal. No information in the conventional sense is being sent. If it were, it would be violating Einstein's cosmic speed limit, the speed of light, which is the foundation of our understanding of the universe. So if it's not a force and not a signal, what is it? The answer is perhaps the strangest, most beautiful and most challenging concept in all of science. The invisible thread is not a physical object, it is a mathematical one. The connection is called the wave function, the system's recipe. To understand this, we must first back away from thinking about particles as tiny solid balls. A quantum particle, before it is measured, is not a thing at a specific place. Instead, it is better described as a cloud of potential, a smear of possibilities. This cloud is the wave function. The wave function is, simply put, a mathematical description that contains all the information about a quantum system. It is the universe's instruction manual for that particle. For a single lonely particle, the wave function might say, this particle has a 50% chance of being spin up and a 50% chance of being spin down. It exists in a superposition of both states at once. It is a blur of probability. When you, the observer, decide to look at the particle to measure its spin, you are forcing it to make a choice. The act of measurement collapses the wave function. The blur of possibilities solidifies into one single reality. The function updates from 50-50 to 100% spin up. This is strange enough, but it is what happens when two particles are entangled that reveals the true nature of the invisible thread. One system, one identity. When two particles become entangled, something fundamental changes. They stop having individual wave functions. They no longer have their own separate instruction manuals. Instead, they are now described by one single unified wave function. This is the absolute heart of the matter. The two particles are no longer particle A and particle B. They have merged their identities to become system AB. They are not two things, they are one thing spread out over space. Let's imagine the wave function for our entangled pair. That single unified instruction manual doesn't say, particle A is 50-50 and particle B is 50-50. Instead it says, the total spin of this system is 0. Therefore, if particle A is found to be spin up, particle B must be spin down. Or if particle A is found to be spin down, particle B must be spin up. This is no longer a description of two independent objects. It is a description of a single correlated entity. The two particles have lost their individuality. They are just two ends of a single unified reality. This is why spooky action at a distance is the wrong way to think about it. There is no action at a distance. When you measure particle A, you're not sending a signal to particle B. You're simply learning something about the entire single system. Think of it this way. Imagine you have a single magical coin that is spread across a room. You can't see it, but you know it has a head side and a tail side. If you reach into the left side of the room and collapse that part of the coin finding heads, you have not sent a signal to the right side of the room. You have simply learned the orientation of the entire coin. By finding heads on the left, you instantly know the right side must be tails, because they were never two separate things. They were always just two aspects of one object. When you measure particle A and find it is spin up, you have learned something about the entire system AB. The wave function for the whole system collapses. The potential of A up, B down, or A down, B up instantly resolves into the single reality A is up, B is down. Particle B isn't told what to do, it is simply part of the same coin that you just looked at. The invisible thread is the wave function itself, the mathematical fact that they share a single identity. The end of parts. This property has a profound name: holism. Holism is the idea that a system cannot be understood by looking at its parts in isolation. You must look at the system as a whole. In classical physics, we can and do describe everything separately. We can describe the moon without describing the Earth. We can describe a billiard ball without describing the one next to it. Quantum entanglement proves that at the most fundamental level this is not true. You cannot describe particle A without simultaneously describing particle B. Their mathematical descriptions are non-separable. They are literally locked together in the math. You cannot write an equation for A without B being in the same equation. This is what the wave function is. It is the mathematical proof of holism. It is the invisible, non-physical informational framework that connects 2 points in space not by travelling through that space, but by existing as a single definition that covers both locations at once. There is no here and there for the wave function. There is only the system. The distance between them is an illusion, a trick of our large-scale perspective. For the wave function itself, they are in the same place, that abstract mathematical space of possibility where they exist as one. In our everyday world, connections weaken with distance. A shout becomes a whisper. The warmth of a fire fades as you walk away. Even gravity, the mighty force that holds planets in orbit, gets weaker with the square of the distance. It's the most basic rule of our intuition: separation matters. Quantum entanglement breaks this rule completely. The standard theory of quantum mechanics makes a shocking prediction. The link between two entangled particles is perfect whether they are 2 millimeters apart on a lab bench or 2 million light-years apart in different galaxies. The spooky action isn't a signal that has to travel through space and get weaker. It's an instantaneous all-or-nothing connection that exists outside of space as we know it. Entanglement is not just a strange curiosity. For physicists and engineers, it is a powerful resource, much like energy, information, or matter. When two particles are entangled, they stop being two separate things and become a single unified system. What happens to one instantly influences the other, regardless of the distance separating them. This connection, which Einstein famously called spooky action at a distance, is not just a puzzle to be studied, it is a tool to be used. It allows us to perform tasks that are completely impossible in the world of classical physics. By harnessing this spooky connection, we are building a new generation of technology that operates on the fundamental rules of the universe. Let's explore the practical, real-world applications of this incredible quantum resource. Ungdom mot fun foi hua to QKD. In our modern world, security is based on mathematics. When you send your credit card number to a website, it is encrypted using a key. This key is based on a mathematical problem that is very hard for normal computers to solve, such as finding the prime factors of a huge number. We are safe because it might take a classical computer thousands of years to guess the key. The problem is, hard does not mean impossible. A powerful new computer or a future quantum computer might one day be able to solve these math problems very quickly, making all of our encryption useless. Quantum key distribution. QKD offers a new kind of security. Its guarantee is not based on hard math, but on the fundamental laws of physics. Here is the core principle. The universe does not allow you to observe or measure a quantum system without disturbing it. The very act of looking changes what you see. Entanglement allows us to use this principle to create a perfectly secure communication key. Imagine Alice wants to send a secret key to Bob. They can use a source that sends pairs of entangled particles like photons in opposite directions. Alice gets one particle and Bob gets the other. Alice and Bob agree to measure their particles in certain ways, for example measuring the spin or polarization. Because their particles are entangled, their results will be perfectly correlated. If Alice measures up, she knows Bob must have measured down. They do this many times and write down their results. This string of ups and downs, which they can translate into a string of zeros and ones, becomes their secret key. Now what if an eavesdropper Eve tries to intercept the key? To read the particle being sent to Bob, Eve must measure it. The moment she does, the laws of physics take over. Her measurement destroys the particle's original quantum state and, more importantly, breaks the entanglement between Alice's particle and Bob's. When the new altered particle finally reaches Bob, it is no longer entangled with Alice's. When Bob measures it, his result will be random. It will not be correlated with Alice's result. How do they know Eve was there? After they have generated their long key, Alice and Bob simply compare a small sample of their key bits over a public channel like a phone call. If their samples match perfectly, they know the key is secure. If they find errors and mismatches in the sample, they know an eavesdropper was listening. The spooky connection was broken and the spies detected immediately. They simply discard the compromised key and try again, perhaps on a more secure channel. QKD makes security absolute. You cannot steal the key without leaving behind a footprint that proves you were there. Ungdung 5-in, Tailung 2 quantum teleportation. First, we must be very clear this is not the teleportation you see in Star Trek. We are not beaming matter from one place to another. We are not moving atoms. Instead, quantum teleportation is a way to transmit the information stored in a quantum particle. its exact fragile quantum state from one location to another without the particle itself ever making the journey. This is a much bigger deal than it sounds. In the quantum world, there is a fundamental rule called the no-cloning theorem. It states that it is impossible to create an exact copy of an unknown quantum state. You cannot just scan a particle and email its properties. The moment you try to scan measure it, you destroy the very state you are trying to copy. So how do you move a state if you cannot copy it, you teleport it? This process requires two things. 1, a shared pair of entangled particles, and 2, a classical communication channel like a phone or internet connection. Here is the process, step by step. The setup: we need 3 particles. Alice has particle 1, the particle whose state she wants to teleport, and particle 2. Bob, who is far away, has particle 3. The resource before the process starts: particle 2 and particle 3 are entangled with each other and sent to Alice and Bob respectively. They now share this Suki resource. The measurement. Alice wants to send the state of particle 1 to Bob. To do this, she performs a special combined measurement on both of her particles, particle 1 and particle 2, at the same time. The result? This measurement gives Alice a classical result like 00 or 10, and crucially it destroys the original state of particle 1. The information has been removed from her particle, the spooky part. The instant Alice does her measurement, the entanglement instantly changes the state of Bob's particle 3. But the state is not quite right, it's scrambled. The classical channel. Alice must now send her measurement result, the 00, to Bob over a normal classical channel. This part is not faster than light. Bob has to wait for her message. The unscrambling Bob receives Alice's message, e.g. 00. This message is an instruction manual. It tells Bob exactly how his particle is scrambled. Based on her message, he performs a specific operation like flipping the particle's spin to unscramble his particle 3. Success. After Bob applies the correction, his particle 3 is now in the exact identical quantum state that Alice's particle 1 used to be in. The original state has vanished from Alice's location and appeared at Bob's. The information, the quantum state, has been teleported. The true power of quantum mechanics is most visible in the race to build a quantum computer. A classical computer works with bits. A bit is a simple switch that can be either a 0 or a 1. Your phone and the laptop perform all their magic by flipping billions of these simple 0 or 1 switches. A quantum computer uses qubits. Thanks to superposition, a qubit does not have to be just 0 or 1. It can be both at the same time in a blend of probabilities, for example 30% 0 and 70% 1. This is powerful. If you have 2 qubits, they can represent all 4 possible combinations 000 or 11011 all at the same time. With just 300 qubits in superposition, a quantum computer could simultaneously process more values than there are atoms in the entire known universe. But superposition by itself is just a curiosity. It creates a vast parallel workspace, but how do you control it? How do you make those qubits work together to solve a problem? The answer is entanglement. Entanglement is the connector that links all the qubits together into a single massive computational system. When you entangle your qubits, their individual fates are tied together. An operation performed on one qubit will now have a coordinated effect on all the other qubits it is entangled with. This combination is what creates the massive parallel processing. Imagine you're trying to find the one right answer in a library with a billion books, a complex problem. A classical computer would have to read book 1, then book 2, then book 3, one at a time. A quantum computer using superposition can essentially read all 1 billion books at the same time, but it is entanglement that allows it to understand the connections between all the books. A quantum algorithm is designed to use these connections to make all the wrong answers. The wrong books cancel each other out while making the right answer. The correct book gets stronger and stronger. When you finally measure the system, the superposition collapses. All the parallel possibilities vanish and you are left with high probability holding the one correct answer. This power to explore a vast space of possibilities all at once, using entanglement to connect them, is why quantum computers promise to revolutionize fields like medicine by simulating new molecules, materials, science, and artificial intelligence. If you have 2 twin coins, 1 heads and 1 tails, in a single entangled state, you can put them in separate boxes. You can give 1 box to an astronaut flying to Mars. The very instant the astronaut opens her box and sees heads, you know back on Earth that your coin is tails. The vast distance of space between you did absolutely nothing to weaken that perfect anti-correlation. The connection didn't stretch or get thin. It was simply there, a single fact, 1 heads, 1 tails, shared across 2 locations. For decades, this was a mind-bending theory, but in the 21st century, we have begun to prove it, from the lab to the stars. Testing this distance independence is incredibly difficult, but not for the reason you might think. The enemy isn't the distance itself, it's everything between the 2 points. The quantum state of a particle, especially a tiny photon, a particle of light, is exquisitely fragile. If an entangled photon bumps into a single air molecule or gets absorbed by a millimeter of glass, the spooky connection is broken. This is called decoherence. The quantum state leaks into the environment and the magic is gone. For years, scientists fought this battle on the ground. They used fiber optic cables, the same kind that bring internet to your home, to send entangled photons. First, they sent them across a lab. Then they sent them across a city using the dark fiber unused cables of the commercial telecom network. Teams in places like Geneva, Switzerland managed to send entangled photons over tens and eventually hundreds of kilometers. But they all hit a wall. Fiber optics, while very clear, still absorb a little bit of light. Over a long enough distance, the chance of the photon making it through drops to zero. You can't just amplify the signal like we do with internet data, because to amplify a quantum particle, you first have to measure it. And as we know, the moment you measure it, the entanglement is broken. How could we test this over truly vast distances? The answer was to leave the ground. The single best way to send a photon a long way without it bumping into anything is to send it through the vacuum of space. This led to the Mikius satellite. Launched by China in 2016, Mikius, named after an ancient Chinese philosopher, is a satellite dedicated to quantum science. It's essentially a high-tech crystal in orbit capable of generating millions of entangled photon pairs per second. It then beams these photons down to Earth using precision lasers. In a landmark experiment, Mikius sent one photon of an entangled pair to a ground station in Delinga, and the other photon to a ground station in Lijiang. These two observatories are separated by over 1,200 kilometers, about 750 miles. As the photons streamed down from space, the two teams measured their properties like their polarization, over and over millions of times. When they later compared their notes by calling each other on the regular classical internet, the results were staggering. The correlations were still there, as strong and perfect as if the photons were in the same room. They had decisively passed the Bell test, proving that the spooky connection was real and undiminished by over 1,000 kilometers of separation. Mikius proved that entanglement is not a delicate short-range laboratory trick. It is a fundamental feature of reality, robust enough to cross cosmic distances. Is space an illusion? The results from Mikius and other experiments force us to ask a truly profound and philosophical question. If the connection between two particles doesn't care about the 1,200 kilometers of space between them, then what is space? In our classical view, space is the fundamental stage. It's the empty box that contains the universe. It's the very definition of separation. But entanglement suggests that on a deeper quantum level, these two separate photons are not separate at all. They are still part of a single unified object. This leads to a radical idea: perhaps space is not fundamental. Perhaps space and even time is an emergent property. An emergent property is something that doesn't exist at the micro level but emerges at the macro level. A single molecule of H2O isn't wet, but put trillions of them together and the property of wetness emerges. A single neuron in your brain doesn't think, but connect 86 billion of them and consciousness emerges. What if space-time itself is like this? What if the fabric of the universe is just an illusion created by a much deeper hidden reality? And what if that deeper reality is built from entanglement? Imagine the universe as a vast, infinitely complex network. Every point in this network is a quantum bit. The connections between them aren't tunnel but entanglement. In this view, two particles that are highly entangled are at this deep level right next to each other. The distance we see in our 3D world is just a rough large-scale map of this entanglement pattern. Two particles that are not very entangled like your phone, and a random atom on the moon we perceive as being far apart. The two photons from the Mikius satellite, despite being 1,200 kilometers apart, were still touching in this fundamental network. EPR sewing space-time with wormholes. This speculative idea has a fascinating name in theoretical physics: ER equals EPR. This is an equation but also a powerful conjecture that attempts to unite our two greatest theories of the universe. EPR stands for Einstein, Podolsky and Rosen. This is the famous 1935 paper that first described entanglement. So in this equation, EPR stands for the spooky quantum link entanglement. ER stands for Einstein and Rosen again. This refers to the Einstein-Rosen bridge, which is the formal scientific name for a wormhole. A wormhole is a theoretical shortcut or tunnel through the fabric of space-time connecting two very distant points. The equation ER equals EPR proposed by physicists Leonard Susskind and Juan Maldatina suggests the two concepts are the same thing. It claims that any two entangled particles EPR are literally connected by a microscopic wormhole ER. This is a breathtaking idea. It means the spooky connection isn't spooky at all. It's a physical bridge. The reason the two particles can communicate instantly is because through this tiny wormhole they are not separated. They are touching. The inside of the wormhole is the connection. When Miccius created two entangled photons and sent them 200 kilometers apart, this theory says it was also stretching a tiny wormhole to be 200 kilometers long. The photons remained connected because they were the two mouths of the same tunnel. If this is true, it changes everything. It suggests that the fabric of space is not a smooth, empty sheet. Instead, it's a foamy construction stitched together by quadrillions of these microscopic wormhole entanglement links. Gravity itself, the force that bends space-time, might just be the large-scale statistical effect of all these quantum connections. In this view, entanglement doesn't just exist within space. Entanglement creates space. It is the thread from which the entire cosmos is sewn. This is the central, deepest and most uncomfortable question in all of quantum mechanics. It is the dividing line between the math and reality, and it has haunted physicists for a century. We call it the measurement problem. Let's be very clear about the conflict. On one side, we have the beautiful, smooth and perfectly predictable evolution of the wave function as described by the Schrödinger equation. As long as we don't look, a particle or a system happily exists in a superposition, a blurry combination of all its possible outcomes at once. The electron is in all places. The atom is both decayed and not decayed. This is the math and it works perfectly. On the other side, we have what happens when we do look. The instant we try to measure the system, that beautiful blurry wave function seems to collapse. It snaps from a cloud of possibilities into one single definite reality. We never see a blurry electron, we always find it at one specific spot. The atom is decayed or it is not. The measurement problem is the gap between these two processes. Why does the universe follow one rule, the smooth Schrödinger equation, when we aren't looking, and a completely different rule, the sudden random collapse, when we are? What is a measurement? This simple question is where the trouble begins. What counts as a measurement? When does the universe decide to collapse the wave function? Let's imagine an electron in a superposition of spin up and spin down. We use a detector to measure it. When the electron hits the detector's screen flashes up. The collapse has happened. But when did it happen? Was it when the electron interacted with the first atom in the detector? But that atom is a quantum object too. Shouldn't the electron and that atom also become an entangled system? Electron up and atom measured up, plus electron down and atom measured down. Okay, maybe it's when the signal from that atom travels to the computer screen. But the screen is also just a large collection of atoms. Why isn't the entire detector in a superposition of screen shows up plus screen shows down? This chain of logic is called the von Neumann chain. You can keep pushing the collapse further and further back. Does it happen when the light from the screen enters your eye? When the signal hits your optic nerve, when your brain processes it? This led some early physicists like Eugene Wigner to a strange idea. Does consciousness cause the collapse? Does the universe need a conscious observer to become real? Most physicists today find this a very unsatisfying answer. Why should the universe care about a human brain? A computer can record the result. Does a camera collapse the wave function? Does a rock? This dividing line between the quantum world, where superpositions are normal, and our classical world, where they are not, is called the Heisenberg cut. The measurement problem is fundamentally that we do not know where to draw this line. This confusion is perfectly captured by Schrödinger's famous cat-in-a-box thought experiment. The experiment links a quantum event, an atom decaying to a macroscopic outcome, a cat's life. If the atom is in a superposition of decayed plus not decayed, and the cat's fate is tied to it, then the entire system should be in a superposition of dead cat, decayed atom plus alive cat and not decayed atom. But this is absurd. A cat cannot be both dead and alive. The measurement happens when we open the box and look. But why is our look so special? What is happening inside the box before we open it? The spooky nature of collapse. The collapse isn't just strange, it's spooky. As we saw with entanglement, this collapse appears to be instantaneous and global. When you measure one particle in an entangled pair, its partner, even if it's on the other side of the galaxy, instantly collapses into the opposite state. This spooky action at a distance seems to violate the cosmic speed limit, the speed of light set by Einstein. It suggests that the wave function, which was spread across the galaxy, somehow knows to collapse everywhere at once. This adds to the mystery. Not only do we not know what a measurement is, but the process of collapse itself seems to break other rules of physics, trying to find an answer. This problem is so profound that it has split physics into different interpretations. They all use the same math, the Schrödinger equation, and get the same results in experiments. But they tell wildly different stories about what is happening behind the scenes. 1. The Copenhagen interpretation. This is the classic interpretation developed by Niels Bohr and Werner Heisenberg. It is the one taught in most physics classes. Its answer to the measurement problem is simple but deeply unsatisfying. The collapse is real, and we shouldn't ask why it happens. In this view, the wave function is not a real physical thing. It is just a mathematical tool. It is a statement of our knowledge about a system. The superposition of dead plus alive for the cat doesn't mean the cat is really dead and alive. It means we do not know if the cat is dead or alive. The collapse is simply the moment we gain knowledge. It's the moment of updating our information. The measurement happens when a quantum microscopic system interacts with a classical macroscopic measuring device. Critique. This interpretation creates the Heisenberg cut by force. It says there is a line between the quantum and classical worlds, but it refuses to say where that line is or why it exists. It solves the problem by declaring it a non-problem. Many physicists famously hated this, with Einstein asking, "Do you really believe the moon is not there when you're not looking at it?" 2. Decoherence. The environment as the observer. A much more modern and mathematical approach is decoherence. This idea doesn't fully solve the measurement problem, but it explains a huge part of it, why we never see macroscopic superpositions like a dead and alive cat. The core idea is that no system is ever truly isolated. The cat in the box is not just cat plus atom, it is also interacting with the environment. Billions of air molecules are bouncing off the cat. Photons, light particles are bouncing off it. Heat is radiating from its body. The box itself is touching the cat. A quantum superposition is an incredibly delicate state. To exist, all the parts of the wave function must stay in perfect alignment or coherence. Decoherence is the process of this alignment being destroyed by the environment. Every air molecule that bounces off the alive cat part of the wave function becomes entangled with it. A different set of air molecules bounces off the dead cat part. In a fraction of a nanosecond, the information about the superposition leaks out and gets hopelessly scrambled with the state of trillions of particles in the environment, the air, the box, the rest of the universe. The environment is measuring the system constantly. As a result, the alive cat and dead cat parts of the wave function can no longer interact or interfere with each other. From our perspective, the superposition has faded away. The cat looks like it is in a definite state, either dead or alive, simply because it is impossible to separate it from its environment. What it solves? Decoherence beautifully explains why we don't see quantum weirdness in our big classical world. The world looks classical because decoherence is happening everywhere all the time, almost instantly. What it doesn't solve? This is the key. Decoherence turns the alive plus dead superposition into a statistical mixture of alive or dead. It explains the fading of the quantumness, but it doesn't explain why when we look we see one specific result. Why did we end up in the alive branch of the universe and not the dead one? It has just pushed the problem outside the box, leaving the entire universe us included in one gigantic tangled superposition. The collapse of the wave function has been our biggest problem. It's the ghost in the machine, the part of quantum mechanics that feels unsatisfying, almost like a cheat. We have this beautiful, precise mathematical formula, the Schrödinger equation, that describes the wave of possibility perfectly. It tells us all the things a particle could be. But the moment we look, that beautiful wave of many possibilities seems to shatter, collapsing into just one single boring reality. And we had to invent this collapse rule just to make our theories match what we see. It led to endless questions. What is a measurement? Does a cat count? Does a rock? Or does it have to be a conscious human? This problem, the measurement problem, is the crack in the foundation of quantum physics. In the 1950s, a brilliant and bold young physicist named Hugh Everett III came along and looked at this crack. He asked a question so simple yet so radical it would change physics forever. What if we are wrong about the collapse? What if the wave function never collapses at all? What if when we measure a particle, it doesn't choose one path? What if instead the entire universe splits, creating a new branch for every single possible outcome? This is the core idea of the many worlds interpretation. It is perhaps the strangest, most mind-bending, and yet in a purely mathematical sense, the simplest solution to the quantum puzzle. Let's imagine our simple electron again. Before we look, its wave of possibility says it is in a superposition of spin up and spin down. The old Copenhagen interpretation says our measurement forces the electron to pick one and the other, possibility vanishes from reality. Everett said this is wrong. According to Everett, when you make that measurement, the universe itself divides. In one branch of reality, one universe, you, your laboratory, and your measuring device all see the electron as spin up. This universe now continues forward with a spin up electron. But at that exact same instant, a second universe splits off. In this other branch of reality, a perfect copy of you, your lab, and your device sees the electron as spin down. This universe continues forward with a spin down electron. Both outcomes happen, both are completely real. There are now two yous, and both are completely convinced that they are the original, and that their measurement resulted in a single outcome. Neither you can ever see or interact with the other branch. The branches have split and are now for all time separate realities. The wave function didn't collapse, it simply evolved, and part of that evolution involved you becoming part of the quantum system. You became entangled with the electron, and the result was the entire system splitting. This sounds like wild science fiction, but its purpose is to solve our biggest quantum headache: spooky action at a distance. So how does Many Worlds fix the entanglement problem? It does so beautifully. It removes the spookiness entirely. Let's go back to Alice and Bob. Alice is in New York and Bob is in London. They share two entangled particles. We know the setup. If Alice measures sun shear, Bob must get sun down, and if she measures sun down, he must get sun up. The old problem was, how does Bob's particle know what Alice measured instantly, even across the ocean? Everett's interpretation says nothing is known or sent. The correlation is already built into the structure of reality. The moment Alice prepares to measure her particle, the universe is about to branch. Let's follow both branches. Branch 1. Alice performs her measurement. In this branch of the universe, her device clicks and reads spin up. Because of the original entanglement, this entire branch of reality is now one where Alice's particle is up and Bob's particle is down. There is no spooky action. Bob's particle didn't become down because of Alice. It was always the down particle in this specific version of reality. When Bob in London eventually measures his particle, he is simply confirming the nature of the universe he lives in. He will with 100% certainty measure spin down, branch 2. But at the exact same instant that Alice made her measurement, the universe also split into another branch. In the second universe, a perfect copy of Alice measures her particle and gets spin down. The fundamental rules of this branch now mean that the copy of Bob in this universe has the particle that is spin up. When this Bob measures his particle, he will with 100% certainty find spin up. There is no signal. There is no faster than light communication. There is no spooky action. Alice's measurement doesn't cause Bob's particle to change. Her measurement is simply the event that splits the universe. She and Bob, who were once part of one shared reality, now exist in separate branches. The Alice who measured up now lives in the same universe as the Bob who will measure down. The Alice who measured down lives in the world with the Bob who will measure up. The correlation isn't spooky, it's just the universe's way of branching. It's like a road that forks. If you take the left path, you will end up at the left destination. If you take the right path, you end up at the right one. You don't cause the destination to be there, you just follow the path that leads to it. The entanglement set up the two paths from the very beginning. This is the beauty of the many worlds idea. It saves the math. It takes the Schrödinger equation as law and follows it perfectly. It doesn't need to add a special messy collapse rule. The only magic is the smooth, constant, and logical evolution of the wave function. But as the prompt says, this solution comes at a very high price. It's not a price in logic or mathematics. In fact, it's the cleanest theory. The price is in our intuition. The cost is the forest of realities. If this theory is true, then the universe is branching, splitting into new worlds every single femtosecond. Every single time a quantum event happens, which is constantly everywhere, new universes are born. There is a universe where you decided not to read this sentence. There is a universe where the light particle from your lamp bounced off your hand in a slightly different way. There is a universe where a cosmic ray zapped a different piece of DNA, and billions of years ago the dinosaurs never died. This isn't just a few worlds. It's an almost infinite, uncountable multiverse of parallel realities, a forest so dense and vast that our own universe is just one single tiny leaf on one single branch. This is the grand and terrifying bargain of the many worlds interpretation. To solve a tiny paradox about spinning electrons, it forces us to accept a reality that is infinitely larger, stranger, and more populated than we could ever have possibly imagined. It suggests that every possibility, no matter how remote, is not just possible, it is real, happening right now in a world that is just as solid and real as our own, but forever just beyond our reach. Our journey into the quantum world began not with a flash of understanding, but with a profound sense of unease. We started by looking at a concept that seemed to break the very rules of the cosmos, a spooky action at a distance that defied all common sense. It felt like a ghost in the machine of physics, a puzzle so strange that it made even the greatest minds uncomfortable. But as we have travelled deeper into this mystery, that feeling of anxiety has slowly transformed. The discomfort has given way to awe. We have moved from seeing a problem that needed solving to witnessing a magnificent picture that was slowly revealing itself. This journey has not been about finding simple answers, but about learning to accept the profound and beautiful complexity of the universe we inhabit. We have arrived at a place where the strangeness is no longer a bug to be fixed, but the main feature of reality itself. Let us recall that initial shock. The very idea of quantum entanglement is an offence to our everyday experience. Our minds are built to understand a world of cause and effect, a world where things are either here or there. If you push a book, it moves. It does not and cannot cause another book in a different city to instantly move as well. This fundamental rule, which scientists call locality, is the bedrock of our intuition. Entanglement tears this bedrock apart. It presents us with two particles, perhaps born from the same event, that remain mysteriously linked. They behave as a single entity, even when separated by continents or in theory by entire galaxies. When we measure a property of one, its spin for example, finding it to be up, we instantly know faster than light itself could ever travel that its partner is down. This instantaneous connection is what felt so wrong. It seemed to violate the universe's ultimate speed limit, the speed of light. For decades it was hoped that this was just a sign that our theory quantum mechanics was incomplete. Surely there had to be some hidden information, some local variables that the particles carried with them from the start, like two envelopes each containing a secret pre-written instruction. But experiment after experiment, most notably those testing the ideas of John Bell, slammed that door shut. The universe is not playing with a hidden deck of cards. The connection is real. The spookiness is real. And so our journey forced us to a new sure acceptance. We must accept that the universe at its deepest and most fundamental level does not play by the rules our intuition wrote. This acceptance brings us to a monumental shift in perspective. Entanglement is not a flaw in the theory. It is not an exotic rare sideshow that happens only in sensitive laboratories. We are now beginning to understand that it is in fact the foundation of reality itself. We have spent centuries building a picture of the world based on reductionism, the idea that if you understand all the smallest parts, atoms, particles, you can understand the whole. Entanglement tells us this is fundamentally backward. The universe is not built from separate things. The things themselves, the particles, are more like secondary concepts. The primary reality is the connection. The universe is not a collection of objects. It is a single vast network of relationships. What we see as an independent particle is perhaps just a localized knot in this universal web. Its properties are not its own. They are defined by its relationship to everything else it's entangled with. This is not just philosophy. It is changing how we see everything. It suggests that holism, the idea that the whole is greater than the sum of its parts, is not a vague spiritual concept, but the core operating principle of physics. When we truly grasp this, the basic concepts we use to navigate our world begin to dissolve. The most immediate casualty is separation. If two particles can act as one system while on opposite sides of a galaxy, what does it truly mean to be separate? The idea of individuality, of a self-contained me and a separate you, becomes a high-level approximation, a useful illusion for the classical world but not the fundamental truth. At the quantum level, there are no fences. This in turn mortally wounds our concept of space. We think of space as the ultimate divider, the empty stage that separates objects. But entanglement shows a connection that is completely indifferent to space. The connection does not travel through space from particle A to particle B, it simply is existing somehow outside of it. This has led many physicists to wonder if space itself is not fundamental. Perhaps space and even time are emergent properties like the wetness of water, which is not a property of a single H2O molecule, but a collective behavior of many. Perhaps the real universe is an abstract, timeless, spaceless realm of pure information, and what we experience as space is just our limited human perception of how those bits of information are connected. Finally, entanglement challenges the very idea of a single objective reality. Quantum mechanics tells us that before a measurement, a particle exists in a superposition of all its possibilities. It is in a way both up and down at the same time. It is our act of looking that collapses this cloud of potential into a single concrete reality. But if two particles are entangled, our act of measuring particle A here instantly collapses the reality of particle B over there. What does this mean? It suggests that reality is not a static thing out there waiting to be discovered. It is a dynamic participatory process. We are not just passive observers of the universe. We are in a small but fundamental way co-creators of its reality with every observation we make. And so we end where we began, in the presence of a deep and wondrous mystery. But it is no longer the spooky, unsettling mystery we first encountered. It is the profound, beautiful mystery of the universe that is far more interconnected, subtle and strange than we ever dreamed possible. We are not separate observers looking in from the outside. We are ourselves part of this quantum weave. Every atom in our bodies is linked to the history of the cosmos, a participant in this grand unfolding quantum story. We are woven from the very connections we have spent this time studying. To be human is to be a small thinking, feeling part of this indivisible whole. We live our lives floating on a vast hidden ocean of invisible connections, and the true beauty lies not in having all the answers, but in finally humbly recognizing the boundless depth of the water beneath us.